Hello again, AP Physics students. In today's lesson, we're going to look at uh, a law referred to as the Biot-Savart Law, which in my opinion is probably one of the most difficult concepts to understand in the AP Physics program. The reason this law is just so difficult to deal with is that you need to have like a very good understanding of all the different hand rules. You need to have a very good understanding of integration. You need to have a very good understanding of some vector math, including the cross product and unit vectors. And also just the problems tend to always occur in 3 dimensions. So just like viewing things in 3 dimensions and setting up particular variables can be quite difficult to do. So just a bit of a warning in advance in my opinion, I think this is one of the toughest concepts in the entire course. Okay, so let's get into it. That said, consider a wire that has a length L with a current I and with DL representing an infinitely small length of the wire. Okay, so I have a straight current carrying wire that has a current of capital I running through it. It has a length that's L, and DL is just going to represent a really small chunk of the wire. Now, just a reminder in terms of like what the direction of DL is, or the length vector, it always points in the direction of what the current is. So therefore, DL would be pointing towards the bottom of the page because that's the direction the current points in the diagram that I see. So DL directed in the negative y direction. We want to figure out what is the magnitude, or we want to figure out what is the magnetic field at point P due to that little differential element. So that's what we're going to attempt to do here. We want to determine the magnetic field, dB, produced just by this differential length element, not for the entire wire. We're not going to worry about that yet. We'll deal with that once we get to the example problem. We'll look at what the entire magnetic field is due to every single one of those little tiny DL contributions. But for now, we just want to get an equation for what is the magnetic field due to this single single chunk of the wire, DL. And we're going to define R as being the distance from the little chunk of the wire, DL, to position P. And we're going to, not only are we going to define it as a distance from the chunk of the wire to point P, we're also going to define R as in terms of a vector. So it's a vector that's going to start at your little chunk of the wire DL, and it'll point towards point P. Therefore, I can see in the diagram that that vector points down and towards the right from the perspective that we're looking at. Now, it turns out the Biot-Savart law actually gives us the equation of what this is going to be. So it allows us to determine the magnetic field due to a wire that has current running through the wire. So I said here a continuous current distribution. In differential form, this is what the law is stated as, and this is actually on the formula sheets. This is not something you need to memorize, so we can just simply go ahead and just start with the equation in this format. Now, the equation is a nightmare. So you have dB is equal to mu naught over 4 pi multiplied by I, which is the current in the wire, and then you have the vector DL, and again, the vector DL points in the direction of current, and then the cross product of R, that little tiny hat on top of it, that R, the hat on top of it, is referred to as a unit vector, and then we divide by just the distance R squared. So just to remind you in terms of what a unit vector is, so if you have that little hat on top of the variable, again, it's an indication it's a unit vector, and a unit vector points in the same direction as the vector that it shares the variable with. So the position vector r points down and towards the right, the unit vector is also going to point in that direction. The difference is the length of the unit vector. So a unit vector has a unit length. A per unit length would just be a length of 1. So if you look at the magnitude of the unit vector r, it would be equal to 1. And if we were to sketch that on the picture, my unit vector, r hat, would point in the same direction as the vector r, except it has a length that would just be 1 unit. Okay, so let's try to expand this equation to determine what the magnitude of dB is at point P. So the magnitude of dB is just the magnetic field due to that one chunk of the wire that has a bit of current running through it. So the good thing is that if we just find the magnitude of this vector, we're not actually going to have to fully evaluate a vector cross product. So we've never really had to do that in the course. I showed you earlier how to evaluate a vector cross product in its entirety, which involves setting up some like 3x3 grids typically, and then doing some vector multiplication, which is extremely tedious. But if we look at the magnitude, it's actually not bad to do. Okay, so I want the magnitude of dB. So the magnitude of dB would be the magnitude of everything that we have stated in the Biot-Savart law. So we have mu naught over 4 pi, and then I, and then the vector cross product of dl with the unit vector r divided by little r squared. Most of the variables in this equation are not vectors except for dl and r. So everything that's not a vector, we're just going to pull it out of the absolute value sign, in which case I would have dB is equal to mu naught I divided by 4 pi r squared. And then we just want to figure out the magnitude of the cross product between dl and r, the unit vector. The magnitude of the cross product between two vectors, and then you can take a look at your formula sheet in the event that you've forgotten what this looks like. It's just the magnitude of the first vector times the magnitude of the second vector multiplied by sine theta. So this would turn into mu naught times I divided by 4 pi r squared, and then the magnitude of dl multiplied by the magnitude of r multiplied by sine of theta. We can simplify this a little bit because the magnitude of any unit vector is just equal to 1. Therefore, we get an equation for what's the magnitude dB. So the magnitude of the magnetic field due to that small little chunk of the wire that has a current I passing through it would be equal to mu naught I divided by 4 pi r squared, and then multiplied by dl, and multiplied by sine of theta. Now, even though we got rid of the unit vector r, it's important to understand what direction the unit vector r points because that's going to establish what theta is. In this equation, theta represents the smallest angle between dl. So again, dl is just a vector that is along the length of the wire that points in the direction of current. So again, in our picture, that was towards the bottom of the page. And then r hat is the direction of the unit vector. So we need to know what direction the unit vector points in order to determine what this angle is. Although the direction the unit vector points is just the same thing as that position vector that points from our little chunk of the wire to where point P was located. So that's my magnitude. Now, I also want to get the direction of the magnetic field at point P due to this little small chunk of the wire. Now, here's where it starts to get complicated just in terms of like the perspectives of looking at things, because like everything's occurring in 3 dimensions. So what I've said here is to get the correct direction, let's view the loop from a perspective where the vector dl is either into or out of the page. So what I'm going to do here is I'm just going to change the perspective. We're looking at the wire, and we're going to look at it from as if we're on top of the y-axis looking straight down. So we'll look at a top view perspective of what the wire would be. Okay, so if we were to show this from a top view perspective, we'd have point P a little bit over towards the right on the x-axis. And then from a top view perspective, since DL is pointing in the negative y direction, from a top view perspective, we could show DL as pointing into the page. We use that X to represent that. Now, to get the direction of what dB is at point P, we can use the first-hand rule. So the way the first-hand rule works is, first of all, identify if we're talking about current or electron flow. So here we're talking about conventional current because I see the capital I. So I take my right hand, and with my thumb, I would point it in the direction of the current, which is, from the top view perspective, it would be into the page. And then the curl of my fingers would tell me the direction of the circular magnetic field that would pass through point P. So let's summarize that. Take your thumb and point it in the direction of DL. So again, from the side view perspective on the left, we'd be pointing our thumb towards the bottom of the page. And from the top view perspective, we'd be pointing the thumb into the page. And that's a perspective we'll use here. So if you take your right hand, point your thumb into the page, then the curl of your fingers should be going in a direction that is clockwise. And that's going to allow me to draw a circular magnetic field through point P. So if I draw a circle that passes through point P, because that's the easiest way to figure out the magnetic field, then the direction of the magnetic field at point P would just be tangent to the path of the circle. And again, if you point your thumb into the page and your fingers curl clockwise, and that must mean through point P, you're going to have the direction of the magnetic field pointing towards the bottom of the page. So dB be pointing bottom of the page here. That's from the top view perspective. If we were to view this from the side view perspective on the left-hand side, then we would have the dB vector that's actually pointing straight at us. So it'd be pointing out of the page in that situation. Okay, so that's typically what we do whenever we have a vector cross product. It's often a lot easier just to figure out the magnitude of a vector cross product separately from the direction of the quantity we're attempting to determine. And that's exactly what we did here. And yes, from the side view perspective, dB would be pointing out of the page, which would be represented with a circle with a little dot. Now, we want to apply the Biot-Savart law to something that's a little bit more complicated, and specifically something that Ampere's law would not work for. So we're going to apply this to a ring that has a current that's passing through it. If you were to view this ring from the perspective of like the right side of the page, from the z-axis, then the direction of current through that ring would be counterclockwise. And like I said, you can't really use Ampere's law to do this. I mean, Ampere's law is usually really good at figuring out the magnetic field due to current, but only if you have like really nice symmetrical objects like cylindrical wires that are straight. In the case of a ring, it's not really going to work. So in which case we're kind of stuck using the Biot-Savart law to deal with this. So let's go through how to do this with the Biot-Savart law. So I said, consider a circular loop that has a radius of capital R. It carries a current I in a counterclockwise direction. That's as if we were looking at the ring from the right-hand side of the page. Point P is located at a distance Z from the center of the loop, and it's along the Z-axis. And what we want to do is figure out the magnetic field due to the entire ring that has current moving through it. And again, we want the magnetic field at point P, which is along the Z-axis that passes through the center of the ring that has the circular loop of current. Step one, we need to first of all just deal with what the direction of this would be. So to figure out the direction, we can actually use the second-hand rule to determine the direction of the magnetic field at P. due to the entire circular loop. So I suppose the way to visualize this is you can kind of, I suppose, for a moment, just in terms of direction, think of the loop as being a solenoid that would have loops of wire that kind of expand towards the right side of the page. So the way I would use a second-hand rule is, because we're talking about current, I would use my right hand, and you take your right hand and you curl your fingers in the direction of current. So if you curl your fingers in the direction of the current, which is counterclockwise from the perspective of the right side of the page, you should have your thumb pointing towards the right. Once again, to determine this, use a second-hand rule, which is to take your fingers curled in the direction of the counterclockwise current from the perspective of the z-axis on the right-hand side, and the direction your thumb points will be the direction of the magnetic field at point P, and that's going to be towards the right side of the page. Step 2, I'm going to draw a small chunk of the ring. So we're going to call that a differential arc element, and we're going to give it an arc length thickness of ds. And I'll do it at the very top of the loop. Usually when we draw these differential elements, we don't put them at a position where it's directly along an axis. But in this situation here, it's actually not going to matter where we do this. But for the sake of the derivation, I'm just going to make the differential element at the top of the ring and directly along the y-axis. And again, I can clarify in a moment why it doesn't matter where you draw it. And again, that differential element has an infinitely small arc length that we're going to call ds. So it makes up a small chunk of the total arc length or circumference of that ring. Step 3, I want to draw a position vector from my tiny chunk of the ring, so that's ds, and I want it to point towards point P. Okay, so no problem. On the picture, I can start at ds and have that vector point towards point P. What I also want to do is I also want to identify what does the unit vector look like. So your unit vector r hat points in the same direction as that position vector r, except it just has a length of 1. So if we were to draw this on the picture, my unit vector would, again, point down and towards the right, except it would just have a length that's equal to 1. But it does point in the same direction as that position vector. We also want to write down an equation for what that distance is, the distance r, and an equation for r squared. Now, this is pretty easy to see. We have a right angle triangle, which I suppose I could just quickly illustrate here. So, right angle triangle, this is perpendicular. This goes here. And r would just be the magnitude of that position vector. So I want an equation for r and for r squared. So to do that, we can use these fixed distances that I have. So the one distance, the vertical part of the triangle, would just be the radius of the ring, and then, or the loop, whatever you want to call it, ring or a loop. And then you also have this fixed distance z from the center of the ring to where position P is. So using Pythagorean's theorem, I would have r is equal to the square root of z squared plus capital R squared. Or we can write down an equation for little r squared, and that would be equal to z squared plus capital R squared. I've done both of them here because we're going to have to make use of both r and r squared, and I just want to have equations prepped in advance for when I need to use them. Step 4, I need to know what is the angle between the differential arc length vector ds and also the unit vector r. Now, in terms of what direction is the differential arc length vector, well, that just points in the direction of the current. So if you're to look at the direction of the current at the very top of the loop, the direction of the current at the very top of the loop, we're going counterclockwise. So it'd be tangent to the ring at the very top. Therefore, ds would point towards, from our perspective here, I think it would point in the negative x direction. So if I were to draw this, it might look something like, let's just, let's locate it. It points something like this right here. Okay, so this would be ds. Okay, perpendicular to the circle and points in the direction of the current. If we want to look at this from a top view perspective, the red thing up here represents the differential element, ds, and I have point P here. So at the very top, the direction of that arc length vector, which points in the direction of current at that instant, would be towards the left. And then my unit vector would point along the z-axis towards point P. And then what you can see then is actually you have a right angle between these two. And even though it's kind of hard to see in this picture, that is a right angle. And in fact, it doesn't matter where you draw the differential element, you're always going to get a 90-degree angle between the two of them. So if I drew the differential element down here, at this point, the ds vector would point straight down, and the unit vector would be pointing towards point P, kind of like in this direction, where it would eventually get over to point P. And then once again, those two vectors are perpendicular. So it doesn't matter where you draw it, it's going to be 90 degrees. So theta is 90 degrees. And even if you did it at an in-between type state, it would be the same thing. And this is why I said it doesn't really matter where I draw the differential arc length vector, you're always going to get that same angle. So in this situation, it's actually okay just to draw the differential element directly along the y-axis or the x-axis, because it makes it a bit easier just to identify the geometry of the problem. And yeah, I already said this. I said, in fact, the angle between all of your ds vectors and all of your unit vectors throughout the entire loop will be theta is equal to 90 degrees, which is, we need this angle to be constant if we're going to evaluate this integral properly. Step 5. So what we've done now is we've set up all the work that's necessary to deal with the Biot-Savart law. So we'll start off by writing down the Biot-Savart law as it's written on the formula sheet. So that tells me that, and we'll write it down in terms of magnitude. So for magnitude, we're just going to put everything in absolute value. So I'll have dB is equal to the absolute value of mu naught over 4 pi times I, and the cross product of dl with the unit vector r hat, and then divided by little r squared. If you remove those absolute value signs, then that is the Biot-Savart law, and that we're allowed to start at that point because the law is given to us. We don't need to understand how the Biot-Savart law is derived, just we're going to go ahead and use it. Okay, now, this equation is written in terms of dl. Now, I think L will be fine if we were dealing with like a straight wire that wasn't bent, but because we have like a loop of wire, and we're writing in terms of arc length, we're just going to replace the dl with the ds. And on top of doing that, in the next step, I'm just going to take everything that is not a vector out of the absolute value sign. So this would then be the magnitude of dB. So again, that's just the magnetic field due to that single differential element. And that would be equal to mu naught I over 4 pi r squared, and then multiplied by the magnitude of the vector cross product between ds and the unit vector r. So if we expand that out, the magnitude of any vector cross product is going to be the magnitude of the first vector, ds, times the magnitude of the second vector, r hat, multiplied by sine of theta. We can simplify a little bit here because the unit vector r has a magnitude that's equal to 1, and theta, which is the angle between ds and r, no matter where you are regardless of which differential element you look at, it's going to be a 90-degree angle. So we'd have dB is equal to mu naught I over 4 pi r squared times ds times 1 times sine of 90, and of course sine of 90 is equal to 1. So this would just leave me with mu naught I over 4 pi r squared ds. So what started off as looking really ugly with like the original starting point for the Biot-Savart law is actually starting to become quite simplified now. We'll do a couple of substitutions here though. So we're going to replace r squared, that equation for little r squared we derived in the previous slide. So that's going to be z squared plus capital R squared. And if we do that, we would then have dB is equal to mu naught times I divided by 4 pi. And then we have z squared plus r squared. Okay, let's go to the next slide. So again, we replaced r squared, the entire r squared just with this here. So there's no reason to have like a 2 up here or anything. Okay, now this only gives us the magnetic field due to one chunk of the ring or one chunk of the loop, but we want to figure out the total magnetic field for everything put together. If we go back to step 1, we already identified that of the only magnetic field contributions that are going to matter at the end of the day is the contributions that point in the z direction, because that's the direction of the magnetic field that the second Henry rule told us it was going to be. So we've got to figure out what this is in the z direction. All other components would cancel off. So the magnetic field so of dB in the x direction and y direction, when we add the integral up, they're not going to matter. So we may as well not even consider it right now. And that's what we want to figure out. We only need to figure out what the magnitude of the magnetic field is at point P due to my differential element ds, and we're just going to do it in the z direction. And this is a step that we did in all of our electric field derivations for continuous charge distributions. We only looked at an equation for the components that actually mattered at the end of the day. We didn't have to do it for electric potential because it was a scalar, but because we're looking at a magnetic field here, which is a vector, and electric field beforehand, now we have to worry about it. So to try to figure out what dBz is, again, this is really tough to visualize in 3 dimensions. So what I've said here is we want to view it in a very specific orientation. So we're going to view this loop from the perspective where ds is either into the page or out of the page. So we'll look at this from the perspective of a side view of the loop. So from the perspective of the side view of the loop, we just don't see the x-axis. The x-axis would be coming out of the page and going into the page. So my loop would then be on the left-hand side, and then I'd have point P that would be towards the right. Our differential element is at the very top of the loop. And at the very top of the loop, we had from that other perspective, ds kind of like pointing towards the left. So what that means is from this perspective, ds would actually be pointing out of the page. Now, we want to figure out what the magnetic field is at point P due to that differential element. So once again, we can use the first hand rule to do that. So what I would do is with my right hand, because again, we're talking about current, take your thumb and point it in the direction of the current, which is out of the page. And the curl of your fingers is going to tell you the direction of the circular magnetic field. So in this situation, it would be counterclockwise. So I'm just trying to locate my cursor. Here we go. Okay, so the magnetic field would be counterclockwise. So at point P, it's going to be pointing in a direction that's tangent to the path, which will be up and towards the right from this perspective. Okay, R is the distance from the differential element where point P is located. and dB would be tangent to the circle and pointing in the direction of the magnetic field. So again, that's going to be up and towards the right. We're going to break this magnetic field vector into two components based on the plane that we're looking at here. So we'll break it into a Z component, which would point towards the right side of the page. That's dBz. And we also have the vertical component, which would be dBy. We're going to call the angle between dB and dBz phi. If we go over to the other side of this triangle, we can identify some other like distances. So if you go from like the center of the ring to like the very top where the differential element is located, that would be the distance, the radius of the ring, so capital R. And this horizontal distance would just be the distance from the center of the ring to where point P is, and that's going to be Z. Now, I'm not going to show this, but the radius of the ring here is actually perpendicular to this tangent. And if you wanted to, you could do some like simple angle geometry just to prove that the angle phi is going to be this top angle up here. Now, we just want dBz. So dBz is on the side adjacent of that components diagram. So dBz would be dB times cosine of phi. To get cosine of phi, we can use this right angle triangle. Here, let's do it in different colors so we can highlight it a bit better. Okay, so I can use this triangle to figure out what the angle phi is going to be. So if I write that down, we would have cosine of phi, because I want to replace cosine phi in that equation. So I'd have cosine of phi would be equal to, well, side adjacent would be capital R, and then side hypotenuse would be little r. But we got an equation for little r on the previous slide. So little r is just going to be the square root of z squared plus r squared. Okay, so we can actually like substitute this in. So cosine of phi would be equal to capital R divided by the square root of z squared plus capital R squared. And we're going to sub that into the equation up here. So we'll just replace cosine of phi with this entire part of the equation. And then we'd have dBz is equal to dB multiplied by capital R divided by the square root of z squared plus capital R squared. We're going to make a substitution though, because from the Biot-Savart law, we ended up with that step where we had dB is equal to mu naught I over 4 pi multiplied by z squared plus r squared times ds. So we'll just take this equation and we'll just throw it in right here. And if I do that, I would then have dBz, so again, it's only the z component that's going to matter, is equal to mu naught I over 4 pi times z squared plus r squared ds multiplied by capital R over the square root of z squared plus capital R squared. There isn't a whole lot you can simplify here, except for what's going on in the denominator. So here we have z squared plus r squared. We could raise that to the power of 1. And then here we could write down this square root as being raised to the power of 1/2. So if I simplify this, I would then get dBz is equal to mu naught I capital R divided by 4 pi z squared plus r squared all to the power of 3/2 multiplied by ds. Now we're ready to integrate and figure out what's the magnetic field contribution from every chunk of that loop of wire or ring that we see. Step 7, find the total magnetic field at point P. We're going to integrate both sides of the equation for dBz. And we're going to do it over the entire arc length of the whole loop. So the left-hand side, we're going to integrate from 0 to my total magnetic field of all chunks put together. We're going to integrate dBz. And the right-hand side, I'm going to integrate from 0 to S. Now, S is going to represent the total arc length, which is ultimately just going to be the circumference of the circle, or circumference of the ring. And we're going to integrate mu naught I, capital R, over 4 pi times z squared plus r squared to the power of 3 halves multiplied by ds. Now, it seems like we're going to have to evaluate a really horrible integral, but it turns out that this is actually a really easy integral to evaluate because everything is constant. So mu naught's a constant, the current through the ring's a constant, the radius of the ring's a constant, 4 is a constant, pi is a constant, z is a fixed distance along that axis, so everything can get pulled out. Therefore, we have b is equal to mu naught I times capital R divided by 4 pi times z squared plus r squared to the power of 3 halves. And then we just have the integral of ds evaluated from 0 to s. We don't actually have to evaluate that integral. We just need to understand what that means. And it basically is just saying, take the entire ring, break it into a bunch of small little arc length chunks, ds, add them back together. And what is that? The circumference. Okay, the total arc length is the circumference of the circle, which would just be 2 pi times r. If we substitute that in, we would then have b is equal to mu naught ir divided by 4 pi, then in brackets, z squared plus r squared to the 3 halves, multiplied by 2 pi times capital R. Now, there are some things that do simplify here. So the pi's go away. We can reduce 2 over 4 to a fraction that's 1 over 2. And then we would have b along the axis of this loop of wire is equal to mu naught I r squared divided by 2, and then z squared plus r squared, all to the power of 3 halves. If I want to, I can take this equation one step further. So if you go to the center of the loop, so the center of the loop is where z would be equal to 0, because that's where the z-axis starts, it's the origin. Then, if I go back to this equation where I have b is equal to mu naught I, capital R squared over 2, z squared plus r squared to the 3 halves. If you replace z squared to 0, we can actually simplify this a little bit more, because then what we have is in brackets r squared to the power of 3 over 2. So r squared to the power of 3 over 2, those 2's would cancel, just leaving you with that cube. And then, if you have r cubed on the bottom and r squared on the top, you can actually get rid of the r squared on the top, and you'd be left with a single r on the bottom, which would then give you a really simplified equation for the magnetic field of the center, which is mu naught I divided by 2 times the radius of the loop. And again, to get this equation like that, you have to use the Biot-Savart law to do it, because there's not really a way you can set up Ampere's law that's going to give you ideal geometric conditions to properly evaluate the integral you have to deal with when setting up Ampere's law. So the Biot-Savart law works well here. It's just, like I said, like there's a lot to do to kind of like set up and determine this. Okay, so let's end off by looking at where we started at. So we started off with having a straight wire, and we looked at one differential element on it, which we called dl. And we used the Biot-Savart law to basically get an equation just for the magnitude of a little chunk of the wire at point P. Now, I want to take this a step further now, not a step further, multiple steps further, and I want to figure out, well, what's the magnetic field due to all contributions put together? And then I want to compare it to the results that you would have got from Ampere's law. Now, if you ever had like a question where you need to figure out the magnetic field at point P due to a current carrying wire, you would use Ampere's law. you can use the Biot-Savart law, which I'm going to show you in this example, but it would be like insanity to like use it when Ampere's law can be used very easily for this problem. So I'll just quickly write down what we would have got from Ampere's law. This goes back way to the start of the AP unit on magnetism. So I'll just say, recall from Ampere's law. It basically told us if we have a really big wire and we have a current I running through the wire, and we want to know the magnetic field at point P, which is located a distance r from the wire. We'll assume the wire is so thin that we don't have to worry about the distance from the outside of the wire to the center. The equation we would have got back then was we would have got your magnetic field B is equal to mu naught over 2 pi, and then I divided by R. Okay, now we're going to do it using the Biot-Savart law. I suppose mainly I'm doing this to show you how awful it is if you don't choose to use kind of like Ampere's law in the right situation. Okay, now before we can set up the Biot-Savart law, we're just going to identify some really simple geometry. So let's look at this right angle triangle in that picture. Okay, so we've got a right angle triangle. I'm just going to go a different felt color just so it's easier to see and write this down. Okay, we want to know the magnetic field at point P, which is a distance x along the x-axis. So we're going to call this distance x here. This distance would just be r, which is just the magnitude of that position vector. And this I'm going to call, this vertical length I'm going to call y. Now, that's a variable because depending on which differential element you look at, y is going to vary. But we can at least write down a few equations here for what r and r squared would be. So r squared would be equal to x squared plus y squared. So we'll box that equation because we're going to make use of it later in the problem. And we'd also have r is equal to the square root of x squared plus y squared. And I'm going to identify one other thing, because in the Biot-Savart law, we need to know what sine theta is. And sine theta is the angle between your DL vector and your unit vector. So we can do that right now. So again, your unit vector is a vector that points in the same direction as r, except it has a length that's just going to be 1 unit. So theta, or I think we'll call it, yeah, we can call it theta, sure. Yeah, theta is going to be the angle between those two. So we can immediately here also get an equation for what sine theta is going to be, just so we can use it later on. So we would have sine of theta would be equal to, it would be x over y. Oh, sorry, not x over y, x over r over the hypotenuse. So we'd have sine theta is equal to x over, okay, and r, as you can see down here, is the square root of x squared plus y squared. Just one other thing before I move forward, just kind of, we're going to compare it back to Ampere's law. So I know I said that it's equal to r here. In terms of like the way we set the problem up, this distance from the wire to point P would actually be x. So when we compare it to Ampere's law result at the end, this should be mu naught over 2 pi I divided by x. And the last thing before we get moving forward here is we're going to have to use this integral that we have off of an integration table as well. So in addition to it being horrible using the Biot-Savart law, you'd also have to know this integral from an integration table to solve it. So again, I'm really trying to drill home the point that if you have a situation like this, a straight current carrying wire, and you want the magnetic field due to it, use Ampere's law. Okay, but let's see what happens when we use the Biot-Savart law now. Okay, so let's go back to my other ink color. So let's write the Biot-Savart law down. So my BS law I did that abbreviation intentionally because it gives you my thoughts as to what I think about using the law because it's so horrible. Okay, so we would have dB is equal to mu naught over 4 pi, and then we'd have I, and we'd have dl multiplied by the unit vector r, and then divide by little r squared. We're not going to use dl. If we go back to this picture, the differential thickness is defined along the y-axis. So instead of calling this dl here, I'm actually going to change it to dy. Okay, so it's my infinitely small thickness that's along the y-axis. So what I'll do is I'm going to write this as magnitude. So I'll go dB would be equal to mu naught over 4 pi, and then I dy crossed with r hat, and then we're going to divide by little r squared, and we want the magnitude of that. Okay, let's write down dB, an absolute value, just as dB. So that dB is, let's pull everything out of here that has nothing to do with being a vector. So that's going to be mu naught I over 4 pi r squared. And then we just need to evaluate the vector cross product between dy and unit vector r. So this would be equal to mu naught times I divided by 4 pi r squared. If we evaluate the magnitude of a cross product, it's going to be dy times r hat multiplied by sine of theta. Okay, let's do a few substitutions here. So we can write these out. Okay, first of all, the magnitude of the unit vector is equal to 1. R squared, if we go back, r squared was x squared plus y squared. And sine theta, if we go back, is x over the square root of x squared plus y squared. Okay, so let's rewrite this all out with all these substitutions that have been made. So this would then be dB is equal to, we'd have mu naught I. Instead of writing down magnitude of dy, we'll just write down dy divided by 4 pi x squared plus y squared. And then multiply by sine theta. So sine theta would be multiplication by x over the square root of x squared plus y squared. Okay, I just want to check her here to make sure I'm not missing anything, because it'd be nothing worse than messing this up before we actually try to set the integral up. Mu naught I dy over 4 pi x squared plus y squared. Yeah, we're good. Okay, so now we can simplify the denominator. You can combine x squared plus y squared and x squared plus y squared, the square root of it. So then we would get, I'll write the dy at the end. So I'm going to write down mu naught I x dy divided by 4 pi. And then I'd have x squared plus y squared to the power of 3 over 2. Okay, so again, just double check that is correct. Mu naught I x dy over 4 pi x squared plus y squared to the 3 halves. Okay, now we're ready to do this integral. So the left-hand side, we're going to integrate from 0 to your total magnetic field B of dB. Now, the other side of the equation, we're going to integrate with respect to y. So what this means is we have to identify, like, where does the wire start at and where does the wire end at. Okay, so let's go back to this picture. Okay, so it tells me the full length of the wire would be L. Okay, but the center of the wire would be a position of y equals 0. Therefore, this bottom of the wire here would be negative L over 2. And this top of the wire up here would be positive L over 2. Okay, so that's going to be my limits of integration. So I'm going to have negative L over 2 to positive L over 2. And then we're going to integrate mu naught Ix over 4 pi x squared plus y squared dy. Okay, the left-hand side would just become the total magnetic field, which is B. So no problem there. Right-hand side, let's pull out everything out of the integral that's constant. Okay, mu naught's a constant. The current through the wire is a constant. X is that fixed distance along the x-axis. We can also pull that out. We can pull out the 4 pi. The only thing we can't pull out is this thing in the bottom here. Oh, that should be to the power of 3 over 2. So this would be the integral from negative L over 2 to positive L over 2. And this would just be dy over x squared plus y squared to the power of 3 over 2. Now, we need to use this integral from the integration table to solve that. So I'll write out exactly what the integral is identified as here, or the antiderivative. So that would be b would be equal to mu naught Ix divided by 4 pi. And then this is going to turn into y over, what do we have here? X squared. And then the square root of x squared plus y squared. And we're going to evaluate that from the y position where the wire starts, which is a negative L over 2, and the y position where the wire ends, which is positive L over 2. Okay, so let's see here what we can do. So the x can be pulled out of the evaluation of the integral because it's a constant. So let's move. Okay, let's move this out. And also when you move it out, there's an x on the top and an x on the bottom, so they can just cancel. All right, so, oops, what just happened here? Okay, let's go back to my purple color. Okay, I'm just going to write this on the next slide just because I'm starting to run out of space now. So we can then write this as B would be equal to mu naught I over 4 pi times x, because it was x over x squared. And then we can just evaluate what's left here. Okay, so what's left is it's going to be y over the square root of x squared plus y squared, and we're going to replace the value of y. So that's going to be L over 2 over the square root of x squared plus L over 2 squared, and then subtract negative L over 2 over the square root of x squared plus negative L over 2 squared. Okay, a couple things about this we can simplify. So first of all, the denominators are pretty much the same thing, except in brackets here is positive L over 2, and here it's negative L over 2. But since you're squaring it, like it's actually equivalent to L over 2 squared. So we have a common denominator set up. And then I can combine the numerators because subtracting a negative would just be adding a positive. Therefore, you'd have B would then be equal to mu naught times I over 4 pi times x. And then L over 2 plus L over 2 would be 2L over 2, which would just be L. So then I would have L over the square root of x squared plus L over 2 squared. Now, this doesn't quite look like the equation for Ampere's law. So the Ampere's law equation should be mu naught I over 2 pi x. Well, here's where you need to use another piece of information. It says that the wire is very long. So what that means is that the length of the wire is way bigger than like the distance that point x would be away from the wire. So we can actually do a simplification of the equation if we account for this. So since the wire is very long, what this means is we can kind of compare what's going on in the denominator. So this would mean that L over 2 squared would be way bigger than x squared. Okay, the length of the wire you can think of as like infinite. If it's infinite, then the distance from the wire to point x be really, really small. So we can actually get rid of, so since the wire is very long, therefore, we can pretty much say that x squared is approximately equal to 0. But just in this part of the equation, because we're just doing a comparison here. So this would turn it into, on the next step, again, we'll just get rid of this. Okay, so we can say that's about equal to 0 in comparison to L over 2 all squared. And then this would then give me B is equal to mu naught I over 4 pi x. And then I would have L over, well, let's see what we have left here now. So we'd have L over 2 squared, and take the square root of that. So that'll just leave you with L over 2. Okay, so what would happen here? This L and this L cancels, which is good because the wire is infinitely long, so we can't really have L in there. And then this 2, since we're going, it's a fraction in the denominator, we can actually bring the 2 up here. And if we bring the 2 up here, we can then reduce the fraction with a 4. So we can change that to a 1. We can change that to a 2. And then look what we get. We get B is equal to mu naught over 2 pi, and then I divided by x. Then again, this is only true if it's a really long wire. Again, is that what we had here? Yeah, mu naught I over 2 pi x. And again, doing this, the Biot-Savart Law, including an integral that you would just have to know off an integration table, is just not happening. Okay, it's not practical at all. I mean, it still works to get what the magnetic field is at that point away from the wire, but use Ampere's law because it's easier. Just like with the continuous charge distributions for electric fields, if you can use Gauss's law, use Gauss's law, except in the situations where you just can't do it. Okay, in which case then you're stuck doing the superposition integration method. Just like here, if you can figure out the magnetic field from a current carrying wire using Ampere's law, do it, unless you absolutely cannot. And the one situation where you could not would be this ring thing that you have here. Like you can't really set up Ampere's law to do that. Okay, but for a straight current carrying wire, yes, you absolutely can use Ampere's law. Okay, so that's it for this lesson. And there's actually just one assignment left in the assignment number 7 or assignment number 8 now on the Biot-Savart law. There's one more lesson to go through tomorrow, but we're just going to go through the lesson, and there won't actually be any additional problems to solve related to it. And I will talk to you then.